Okay, in starting registration, I alert everyone, if you don't want to be recorded, of course not the voice, but the face, please turn off the camera, because we record everything in order to have material for see the course again and for other uses.
So now
it's the recording is started.
Okay. And I have and now the next, so the presentation is started on my screen, and now the next step is to share that with you.
Screen, yeah.
Which is where? Schermo intero. Here. I guess it's this one. Okay. Do you see the screen, the refresher?
Yeah.
Now the problem is that I lost the screen of the meeting.
Okay, don't worry, I am here.
Okay, so if you see somebody raising the hand, you will...
No, please don't you raise your hand, speak.
Speak,
turn on
yes.
the microphone and speak.
Yes, that is much better. So as I was saying in the short description of my intervention, this is really for the benefit of those that were exposed to computer science some years ago, or maybe had never been exposed. And I will try, I like very much a historical perspective. So I will start really with the history of computers, and then we will see how they work and really the basics. So so what is the now we have problems because I'm having too many screens. I don't know. Okay, I found the right one. So the first, I mean, the history says that the first real, between quotes, computer was invented and partially built by Professor Charles Babbage in the beginning of 1800. Now, why we say that it was the first one? Because before that one, there have been many computing devices. One of the most well-known is the Pascalina, is a calculating machine invented and built by Blaise Pascal about 100 years earlier. Now, the whole point, and we will get back to this again, is that the Charles Babbage was the first one to design and build something that could resemble a computer as of today, which means that you have a hardware that is able to perform, to execute many different programs. The Pascalina and all other mechanical devices that had been invented before were just, let me say, able only to do the computations that they were built for. So that is basically the reason that this was considered to be the first one. And as I was saying, it was really, he actually built two computers. They were actually used to do real calculations. In recent years, you have seen that we have this Ada Lovelace that has been considered to be the first programmer because she was helping Babbage in programming somehow the computer that he had built. And you might wonder how was working the computer. And the idea was basically based on an idea that had just come out a few years before of the mechanical loom, in which that was the Jacquard that invented this idea. And without entering into the details of the loom, I mean, you know that the loom is done to weave fabrics. And the idea of Jacquard was that you could build a loom in which you were just putting on a punched piece of paper the program, let me say the pattern that the loom was going to design and to draw on the fabrics that was building. So this idea was clearly taken by Babbage, and instead of putting behind, let me say, the program, the paper tape here, an actual loom, he was putting there a mechanism of mechanical gears that were doing the actual computations. And clearly that was all, there was not yet any electricity, so all of that was working on steam. So you may think, why did not really, an industry did not really start from there. However, this idea of the information codified and let me say, and put on punched paper is still alive today, because what we can see is, for example, I don't know if you have ever seen, they are actually, you can see some of them still in France. In Italy, it's a long time I don't see them. The organ grinder, meaning these things in which you hear the music and you have the guy behind turning the wheel, like in this case. And the music is actually codified on punched papers that is really inside the machine. So this is just as I was saying, just to have a glimpse of the past. Now, coming closer to us, for about 100 years, nothing happened. Then, about in the 30s of last century, as they say, the technology was already progressing, the technology in electromechanical devices. And there have been many, let me say, projects. At least 3 of them, let me say, have become stable enough to be considered again the first idea or the first building of a computer in the sense that we have today. Now, those 2, I don't know if you know the name, but those were in the United, let me state it this way. Until recently, it seemed that the computers had been invented, between quotes, just in the US, because outside of projects like the ABC of the Mark I in the US, no one really knew of anything else. Just in recent year, it has come out that also in Germany, and especially on the part of this Konrad Zuse, who was a private entrepreneur, he was actually building machines that were somehow also even more advanced than the ones built in the US universities in terms of, for example, already using the binary notation, using as little mechanical stuff as possible, and so on. However, the point is that all of these research projects at some point were, so to speak, interrupted by the Second World War. And the difference between the US and Germany is that while the US, they really believed that computers could be a very strategic weapon and a very strategic asset in time of war, Germany somehow did not think about that. So Konrad Zuse built, after the Z1, built another 2 machines, the Z2 and the Z3. But again, the government was not really thinking that it was useful work. So that's why somehow the computer industry was born, I mean, started and took off really in the United States. However, the point is that with the arrival of the war, a lot of money was available for this research project, as I was saying before, because the US were really thinking that computers could be a very strategic asset. So I make here the 2 main examples. One is the Harvard Mark I, that is the successor of the Mark I that we have seen before. It had still a lot of mechanical parts, but it was working. And as you can see, I mean, the performance as compared of today is somehow, I mean, that doesn't really even think of as a computer. But if you compare with those, let me say, operations done by hand, you can also see that there was already a big advance in the use of computing machines. Another example is this one. This one was actually used by the Navy to compute the ballistic calculations. I mean to compute how to orient the cannon in order to make a right shot. And this is a very complicated function. And based on what we read, again, if a person or a number of persons would have done those computations by hand, that would have taken, let me say, I think something like 2 hours to compute the new asset between one shot and the other. While with this new, between quotes, computing machine, it was just taking just a few minutes. And here you see, however, we will get back to this figures later, but you see that as compared to what you have in your hand, I mean your smartphone or your PC, we are on a completely different scale, 30 tons, 72 square meters and so on. However, they were working, and they were somehow really the ancestor of the computers of today. The last example of this World War effort, this is the Colossus machine. That this again was unknown to most of the people until the 70s, because it was really a very well-kept secret in London. And now it is very popular because there was a movie. I always forget the name of the movie, but it was the story of the famous mathematicians and logic. Okay, somebody help me with the name. Turing, Alan Turing. So there was a movie about the life of Alan Turing, and Alan Turing was very instrumental in the development usage of this machine, the Colossus, that was used to decipher encrypted German messages. And somebody says that it was just because of this machine that somehow around the 44 the war took another turn. In any case, those are really, the message here is that really in a few years, let me say from 42 to 46, there have been a tremendous advance in the technology of computers, just because there was a lot of money. I mean, the US government was somehow allocating unlimited resources for the development of those computers. And by the end of the war in 1945, there was let me say, the next generation of computers came out with this EDVAC, and there was a paper published. This is considered to be the real first ancestor of computers as we see today, because somehow the big idea of the big advancement that was in this computer was that the program was treated the same way as the data. So you only had one kind of memory, and this memory you could put there both the program and the data on which the program was acting. So this is why in the machines that you have seen before, somehow there was a clear distinction and a clear notion that the computer was able to perform many different programs, because this is the essence of a computer as compared to a calculating machine. But in the previous implementations, the program was somehow stored or treated separately from the data. Instead, this one was the first time that there was this architecture. And the paper was, I mean, the group was led by John von Neumann, and there were other people. However, there was a publication in 1945 that was just describing this new architecture, and was not mentioning the name of John Atanasoff, that instead had already, he claimed, built a machine a few years earlier with the same architecture. So as you can see that now technology and politics and things can mix, because it took about 20 years to John Atanasoff to have officially, let me say, recognized that he was the first one to have invented, let me say, this idea of having the program and the data in the same memory. And what was this idea of John von Neumann? Because this is still called today the von Neumann architecture. is basically this one. This is the basic architecture of a computer. On one side, you have the CPU, the central processing unit, which is the unit which is able to perform computations, not just addition. Basically, however, the computations are basically addition, subtractions, I mean, comparison, and so on. And on the other side, you have the RAM, the random access memory, where this is the real step forward, where you can put here both the data and the program working on this data. Then, of course, you have a control unit, let me say, regulating the exchange of information between the CPU and the RAM. And then you need, again, a way to put into the RAM the data and the memory that you want, the data and the program that you want, and to take out the results of some computation. So this is, and why it is somehow, let me say, so important, because I make here an analogy with the cars, meaning that the computers of today, we are now about 60 years later, 70 years later, still have exactly the same architecture. I mean, the sophistication is that now you have a much more, let me say, capable CPU and RAM and so on. We will see some figures in a moment, but the basic architecture is the same. And the analogy is that I make an analogy with the cars. I mean, the car that we have today, they were, the first one was invented by the end of 1800. Which with the engine, with the combustion engine, and more than 100 years later, I mean, the cars are still working on the same principle, meaning that you need some fuel, and then by burning this fuel, you get the energy. It is exactly the same. Clearly, the technology has evolved a lot, because if you think of the Ford Model T in 1905 and any cars of today, there is clearly a big difference, but it's the same difference that you have between the HVAC and the PC of today. And if we go on, so what is now, why it is called the random access memory? Why the memory is called the random access? Because that means that, okay, what is the memory, first of all, in this view? The memory is just, you can think of an array of cells or words, and each word, these cells are numbered from 0 to n. And the number of the cell is the address. It's called the address of the cell of the word. And it is random because, contrary to the memory devices that were before, you can access every cell, every word of the memory in any random order, meaning at one access you can access word number 2, and the next access you can access word number 1000, and so on. While most of the previous memories were sequential, meaning that in order to access word number n, you had to go through all the words before n, which you can clearly see that was really, I mean, there is a much difference in time. And the way that the memory works, this can be useful to understand later, is that you basically have an address bus. It is called a bus because you need a lot of wires to provide your address. But conceptually, what you do, you provide to the RAM the address of a word. With the control line, you tell the RAM whether it is a read or a write, and if it is a read, when the clock, the command arrives, the content of the cell whose address is on this bus will be made available on the data bus. If it is a write, the data available on the data bus will be written in the word identified by this address here. So this is the basic working of the memory. And
Vittore,
yes.
I think you have to stay a little bit on this slide and ask if someone have something to ask about. Oh, everything is clear, because you explain really fast. Maybe they don't have enough. I don't know if they.
No, but this again is not important to really grasp the details. What is important is to understand the notion that the RAM is a random access. And in this this n, let me say, in these millions of cells, you can store in the same way both the data and the program. And in the next one, what we see is that the way that actually the computer works is this cycle, meaning that each cycle of the computer, the CPU is taking one instruction from the memory, then it executes this instruction, and if needed, some data is extracted from the memory, then the operation is executed, and then the result either remains in the CPU for further elaboration or is written back in the memory. So this is the basic cycle which happens for every instruction. And so that's why, if I go back of one, that's why, I mean, this is basically the way in which the CPU interacts with the RAM, meaning it provides an address to get an instruction. And the instruction is coming over this one here. The CPU executes the instruction, and if the result of the instruction has to be written back in the memory, the CPU will provide the address where to write this result here, will provide the result here, and the result will be stored in the RAM. So this is the way that if you look really inside the computer works. But again, I don't know. In any case, if you see some hand, if somebody rose the hand, let me know. Let me see. I stop here for the moment in this sense. Let me close and I will try to. I'm trying to recover my screen, but I cannot. Okay, so I don't know why I cannot really see. Here it is. Now it is. Now let me try to start again the presentation. What you see on your screen now?
We see your window and the Leaning Tower.
Okay. And now?
Now the slide.
Okay, now I was successful. I was able to take the the window of the meeting from behind the screen. So let's go on. Now, and this is where we will get back. Now, you might wonder if I don't know if you want to wonder, but you might wonder, but when we say about data and information, how it is actually stored in the computers. Well, if we go down to this level of the hardware, the fact is that the computer is basically built with electrical components that are usually able to be in one of two possible states. And we indicate those states with 0 and 1. So that means that at any moment in the memory and in the CPU, all the information is stored and exists as a sequence of zeros and ones. So this is so that means that, and we will say that in much more detail, that all the information that we want to store in the computer has to be transformed into a sequence of zeros and ones, the so-called bits. So this is the basic of the things. Now it's like going back to the analogy of the car, it's like when you open the hood and you look, this is the engine, this is the carburetor, this is the battery, and so on. But then you close the hood again, and as long as the car is working, you don't care too much of the actual things that are inside. So somehow, again, we are now opening the hood, looking what is inside, but really the sequence of zeros and ones, we will see that we don't need to really think to the information in this way. Now, to complete this very quick historical perspective, now, how the computers have evolved in these last 70 years or so. Well, first of all, there is the computer technology. I mean, the components that by which a computer is made. And as I was saying before, the first generation, I mean, in the early 40s, were electromechanical computers. So they had still mechanical part in movement. Then there was a second generation in which the mechanical parts were replaced by vacuum tubes. Vacuum tubes, I don't know if you have ever seen one. They are like small lamps. For example, the early TV sets, early meaning in the 50s, were based on these vacuum tubes. And they have the property that they can switch, let me say again, state from different states very quickly, much more quickly than an electromechanical device. But they still are somehow bulky. As I was saying, a vacuum tube is the size is like a small lamp. And now the big jump was with the third generation, in which the vacuum tubes were replaced by transistors, which were doing the same, had the same electrical properties, but they were solid-state devices, meaning just built on a chip of silicium and with other components. And then we started, let me say, the miniaturization of these solid-state devices, which is I don't remember the first test. In any case, the SI is a scale integration. So it is small scale integration, medium scale integration, large scale integration. And today we are in this fourth generation of VLSI, very large scale integration. And when we say very large scale integration, you can think that on a chip, let's say by 2 centimeter by 2 centimeter, so this is the actual size, you can put there more than 10 million circuits. So this is the way that our smartphones and all the computers are built today. And what has been the consequence of this evolution on the basic technology? Well, the consequence is the one that we are touching today, meaning, first of all, the speed of the CPU has moved from kilohertz to megahertz to gigahertz, which means what? As I was saying before, that the basic cycle of the CPU is to fetch one instruction from the memory, execute the instruction, and store back the result into the memory. So this is one cycle. And the first machine were performing this cycle, so let's say in the order of 1,000 times per second. Then we moved rather quickly to millions of times per second. And today we are at the level of billions of times per second. Again, if you buy a computer today, a PC, you think that when you go and buy a PC, one of the things that you look at, what is the speed of the CPU. And normal speeds today are between 2 and 3 gigahertz, which means that our PC and your telephone, I mean, the telephones are not advertising these things, but they're basically the same, are able to perform about 3 billion basic instructions per second. The same jump was done in the RAM, in the memories, that we went from kilobytes, meaning thousands of bytes. A byte, we will see in a moment, is a packet of 8 bits. So it's a packet of 8 binary digits, or a packet of 8 zeros and ones. It is called a byte. And again, the RAM has moved in the last years even more quickly from kilobytes to gigabytes. Going back to what I was saying before, you would not buy today a PC with less than 4 gigabytes of RAM. Actually, you would prefer 8, and are becoming standard the PC with 6 gigabytes of RAM, which means that your RAM memory has 16 billions of cells, what we were saying before. And the same thing is also for the external memories, in which today the memory stick, I mean, that we are using outside of the computers. Let's forget about the CD and the DVDs that are slowly disappearing. But the memory sticks that we are using today have quickly moved to megabyte to gigabyte. Again, I can make the example of the smartphones, in which today a normal smartphones can have inside a memory stick. It is actually, it's not called a memory stick, but it's called a microcard in the order of 64 gigabytes, 128 gigabytes. They're all normal sizes. And the evolution of the digital world has moved very quickly, because if we look at this table, these are the names of, let me say, the size of digital information. As I was saying, I mean, we started with the key, those are the abbreviations to identify the power of 1,000. So we say mega, but again, mega is really means 1 million, and giga means really 1 billion. And tera really means 1,000 billions, and so on. Then we could go on with Donald Duck and Zio Paperone in Italian, with trillions and things like that. And as I was saying, today it is normal to speak about memory size in the order of the gigabytes, both for the internal memory and the external disk. The external disk now is becoming common to identify with terabytes, meaning thousands of gigabytes. This was, let me say, back one moment. Gigabytes, and again, you would buy an external disk of 1 terabyte. Today you can buy one of 1 terabyte for 50, 60 euros, a little bit bigger one of 2 terabytes with about 100 euros. And in real life applications, we already are talking about petabytes, which means thousands of terabytes. The example that really struck me was that that was already a few years ago. A ground station receiving data from satellites is receiving in the order of about 3.5 petabytes per week. So this is the amount of data that is coming down from satellites to ground stations. But the point is that then when this information is down, you have to store somewhere, you have to process somehow. So, and at least in my mind, I mean, just the notion of a petabyte is already too much. I mean, a terabyte is 1,000 gigabytes. I can still grasp or have an idea. The petabyte is one order of magnitude. It's a little bit more. But in any case, this is what we are dealing today. And so you can see that the number of bits that we are dealing with is really big. There was in parallel also the evolution of software, of course, in which we've started where, I mean, at the beginning, clearly there was one single user for one single computer. Then very quickly we moved to multi-user, meaning that the same computer could be used at the same time by many different persons, and each one had the illusion of being the only user, because the operating system was working this way. Another aspect is the multitasking, meaning that on the same computer, and this is what we are normally doing on our telephone, meaning our telephone is actually is a very powerful PC, and what we are doing is that we are doing multitasking, meaning at the same time we can have the telephone receiving a message, you are talking on the phone, and then you have another window open on a website, and then you receive a telephone call and so on. And so they are all windows, meaning tasks that are running in parallel on the same computer. And another evolution of the software that was, again, historically in the 70s, I would say mostly, was the client-server architecture, meaning that you can have an application that is split on two computers. One computer that is the client of this application and the server providing services to the application on your computer. And this is actually the architecture of the web today. We will see that a little bit better. And then we have the communication, on which we will spend a few words, because this is the essence of the internet and the web of today. I mean, the ability of networking, meaning the ability to exchange information over a network of computers. So now, with this in mind, what has happened over the last 70 years of evolution of computers? Because again, why there has been this evolution that is still going on today? Because the computers have become, after the military applications and the scientific research in the beginning, computers have become a big market, I mean, a big business. So that's why there has still be a lot of money invested in research and a lot of money invested in marketing. And more or less, we can identify what I would call the eras of computers. I was saying, in the years from 1945 to 50, they were still mostly, let me say, research projects in the universities. Then it was the first one I mean, the first big one to see the potential for a market for computers was IBM, International Business Machines, that was already working, however, in this field of providing office equipment and tabulating machines. And however, starting with the early 50s, computers became something, I mean, a market to be sold mostly to industries and to offices. And IBM quickly, in 10 years or so, got the monopoly of the practical monopoly of the market, which went on in the 60s and in the 70s. And it is estimated that in those years, IBM was having more or less 85% of the worldwide market of computers, which was good and bad, because in a sense, I mean, it was bad because a monopoly is never good, but it was also good because IBM really contributed a lot to the advancement of the computer technology. And one turning point in this evolution of computer technology was at the beginning of the 60s, when IBM came out with an architecture called the 360 architecture. That was the one that was somehow inventing the byte. With this architecture, IBM built and sold a series of machines where the internal architecture was such that the information internally was being managed and was being stored in terms of bytes, meaning the minimum amount of information that was handled internally in the machine was a byte, meaning a packet of 8 bits. And the bigger machines of this series were handling, let me say, 4 bytes at a time, 8 bytes at a time, 16 bytes at a time, so that with the same architecture, I mean, with the same program, could really run on all the machines of the series, and without any change in the program. The only change was that if you were buying and using a bigger machine, your program was running much more quickly. So, and this is what's called the mainframe era. Now we see a picture. Now this, let me say, this monopoly of IBM and this monopoly of this big mainframe, really big, all of a sudden, it took a few years, but again, not 10 years, just a few years, started to be changed by the arrival of mini computers in the early 70s. And what were mini computers? Well, mini computers were simply the mainframe, and somebody had the vision or the intuition that all the computing power of a mainframe that was needing, let me say, a room more or less the size of a tennis court, all this computing power could be packed in a small cabinet 1 meter by 2 meter, and it was just performing and offering the same performances as this mainframe. And so there were a number of small companies that started, and those computers clearly did not need water cooling, did not need air conditioning or very strong air conditioning, and most important, were costing 1/10 of the mainframes or even less. So at this point in the 70s, the market started becoming, let me say, more diversified. And the number of computers, let me say, started to increase really quickly. And the other big revolution in this view of the computers is more or less the same revolution in the beginning of the 80s with the arrival of the PC. Now, the arrival of PC means that now we have this, what I call the urban legend, because for this PC, the birth of the PC, we do have names. I mean, Steve Jobs and Paul Wozniak, and they say, which is true, however, that they started their business in a garage building the first computers, what then became in a few years Apple. And I mean, for the mini computers was more or less the same. However, maybe the time was not mature enough. There is no names associated with the inventor of the mini computer. It just came out on the market. With the PC, we do have the name of the inventor again. Steve Jobs and Paul Wozniak, but this was really the biggest revolution, because with the arrival of the PC, the mainframe really disappeared, and the computer market became really fragmented. But even more important, I mean, the users of computers started to be in the orders of millions and billions. And the final, let me say, change in this whole scenario was then at the beginning of the 90s, when let me say, I say the arrival of the internet and the arrival of the web, and this is the scenario that we all see today. And we will get back to this one in a little bit more detail. But from this, it's important to keep in mind, let me say, these 2 points here. I mean, the early 70s with the arrival of the mini computers, and the early 80s with the arrival of the PC, because those are really the 2 things that completely changed the landscape of the computer world and the computer usage. I have just for the benefit of us, I was not there, a brief picture gallery. So this is just to give you an idea how big they were. So this is the Harvard Mark I, the real one. I mean, that was built and was working, was used in war operations. This is the ENIAC. Again, this is you can see they are big, all the wires outside. Then we move on a little bit, and we are in 49. This is when there are no more mechanical parts in movement. Everything is, all of this that you see here are vacuum tubes, like small lamps. And you had, I think, in this sense, like you had about 18,000 of those that were just broken very quickly, and most of the time the operator of the machine were spending their time replacing these things. Then the big jump is in the 60s with the arrival of the first mainframes. So this is IBM mainframe. Those big units that you see here are the external memories. Those are tapes. It's like a cassette tape on a giant scale, because there is tape here and here. And this is the console where you can control everything. If I will remember, this one should be the card reader, I mean the input device. And behind there is the CPU. You can see something like that in the 60s. I mean, the look was a little bit better, but you can appreciate that this is really a big room full of units. And what we do not see here is that underneath, I mean, below the floor, there is a system of water cooling, because in order to increase the speed of the CPU, you wanted to have it water cooled. So this is those are the mainframes, and that was really the point in time in which computer applications really boomed. And then the next revolution was the mini computers. As I was saying before, more or less in this cabinet you have more or less the same computing power that you see here. Because why? Because technology had really advanced to the point that you could miniaturize everything. And you still have the AP units outside, you still have the input-output device, but those are the mini computers. And the last step is the PCs. So those are real pictures of real PC. This is the Apple, this is the IBM, and they are around, I would say, the early 80s. And from then now on, I have no more pictures, because you have on your desk or you have in your hand what are the computers of today. So this is the end of the historical perspective of the evolution of the hardware. Are there any questions? I do not see. Again, interrupt me if you have a curiosity or things. No. Okay. I will go on. With data representation within a computer, this is something that I think it's should be good to know. I was saying before that at the machine level, if we go down, the information is really represented as 2 voltage levels, typically 0 volt and plus 5 volts. Now, clearly, we are not engineers. We don't care about the voltage. So we conceptually, we associate these 2 possible states of the machines to state 0 and state 1. So I mean, our interest of what is inside the computers really starts with the notion that the information in the computer is based on sequences of zeros and ones. And so the next question is, how can we represent all the information, numbers, text, documents, images, video, audio, with zeros and one? Well, the answer is simple, so to speak, in the sense that, first of all, we have to understand how we represent numbers. And now, after we understand how we can represent numbers with these zeros and ones, all the rest comes easily, because we only need to represent text with numbers, documents with numbers, images with numbers, and so on. And we will see quickly how. Now, how can we represent numbers with zeros and one? Let's start from the beginning, what we learned at the school, the elementary school. And we learned that when we see 3, 4, 7, we learned that these are the units, these are the tens, these are the hundreds, this would be the thousands, and so on. So without knowing, we learned to use what is called a positional notation in base 10, because that means that our system of numbering has 10 digits from 0 to 9. And the weight, the value of each of these digits is based on the position it is in the number. So a 7, 4 here is in the position of the tens. A 3 here is the positions of the hundreds, and so on. And these positions are actually the power of the base. So as I was saying, when we see 347, we say 347 without even thinking. But the actual mathematics that is behind is that we immediately recognize that 3 is associated with the power of 2, I mean, with the hundreds. 4 is associated with the tens, and this is associated with the units. Now that we understand the mechanism, and the mathematicians are always willing to experiment, cannot we use a different base? Why use 10 instead of using 8? And actually say 8 because the early computers were using representation of numbers in base 8. Now, the mechanism is exactly the same. In base 8, you have 8 digits from 0 to 7. And the weight of these digits depends on their position in the number. But this time you are reasoning with powers of 8 instead of powers of 0. So the 7 here are the units. The 4 here are the number of eights, not of tens, of eights. The number of years is the 3 here is not the hundreds, but is the 64s, because this is the second power of 8, and so on. And so it is quite easy to see that 347 in octal, this is it was called in octal, not in decimal. 347 in octal is equivalent to 231 in decimal. So now we have got the mechanism, and you can easily imagine, I have another example, but this is because it's very much used in computers. Now, why you not use another base like base 16? Exactly the same reasoning. For a base 16, I need 16 digits that goes from 0 to F. Why is F? Because we need some new symbols to indicate the digits after 9. Because they have to be all different one from the other. And I mean, at the beginning, it was decided that the digits after 9 in a hexadecimal notation were indicated by A, B, C, D, E, F. So those are digits, are not letters. So it was just a convention to decide that the same way that somebody thousands of years ago, or maybe centuries of years ago, decided this symbol here was the 3, this symbol here was the 4, this symbol here was the 5, and so on. For the hexadecimal notation, somebody has decided that this symbol is the 10, this symbol is the 11, and so on, because it should be clear that given the base, you need as many different digits as there are in the base, because then you need to identify all the units of this base. And so we have exactly the same reasoning. Now I have an hexadecimal numbers 3BF. What is this? Okay, we do the same things. Those are the units, so we multiply F by the power of 0, by 16. These are the base, 16, so we multiply B by 16. This is what used to be the hundreds. This is the power, the second power of 16, which is 256. If we make the computation, we see that 3BF in hexadecimal is exactly the equivalent of 959 in decimal. Hopefully I put here again the scale, because while for the tens we do not need any scale, when we go to other bases it is convenient to know what are the different weights in the position. So those are the units, this is the next one, this is the equivalent of the tens, this is the equivalent of the hundreds, this is the equivalent of the thousands, and so on. What counts is really the power of the base. And the last step, as you can imagine, is the binary, which becomes much smaller and smaller in terms of computation, but much longer in terms of digits, because now you need, since each digit has a little weight, you need many more digits to represent a number. But I'm not going to the details again, but if they have the binary number 1011, what is this binary number in decimal? Well, we make the usual computation, so to speak. Those are the units. This is the power of 2. This is the power, the second power of 2, which is 4. This is the third power of 2, which is 8. So 1011 is the equivalent of 11 in decimal. And this is the way that we represent numbers within the computer. And clearly, in order to represent bigger number, we need more bits. This is just, again, you don't need to remember this one, but sometimes it is convenient to remember. So those are the power of 2 from 1 to 256. And so this is a byte, because those means that here, in order to represent this number, you need 8 bits. And therefore, this is the value of a byte. The numbers that you can represent in a byte goes from 0 to 255. And those are the things that you remember when you say, okay, 1 giga. You have a memory of 4 gigabytes. Yes, but how much is 4 gigabytes? 4 gigabytes is 2 to the power of 32, which is about 4 billions, 200 millions, and so on. So those are what I would call the milestones in binary notation. And this is the last one, why I was mentioning hexadecimal, because very often, and this is very much used, you use the hexadecimal notation in order to represent a byte. And here it's the explanation why it is convenient, because if you take, let's see this one. If you take 3 bits, let me try to provide this explanation. With 3 bits, you can represent the numbers that goes from 0 to 7. Now, if you wanted to represent 8, you do not have, let me say, any more room here. It's like on the car machine when your odometer arrives to 99999. Well, the next step is just the zero or the zeros, because you need to add one additional digit to the left in order to move one order of magnitude. So the same is here, which means that with 3 digits, you can represent the number that goes from 0 to 7. Now, if you want to go further, you have to add a 4th bit, and usually you add one in the front. But again, since the bit can have 2 values, you can add the 0 on this side, and they remains 1, 2, 3, 4, 7, and then you put the 1 on this side. But now this one is adding the weight of 8 to all these numbers. So these numbers here becomes 8 plus 1. These numbers here becomes 8 8 plus 0. This number here becomes 8, this 8 here, plus 1, 8 plus 2, 8 plus 3, and so on. And we indicate them with the hexadecimal digits. And this is very convenient because if you want to represent a byte of which you know the binary configuration, like this one, you can divide the byte into 2 halves, and you represent each half with an hexadecimal digit. So this 10101, 1011 in hexadecimal can be represented as 5, because these 4 digits are 5, and B, because these 4 digits are B. And if you happen to deal with, let me say, detailed information at the machine level, the hexadecimal representation is one of the most used. Questions? I do not see any hand. Are you still surviving? Am I going too fast? But again, this is clearly you have to grasp the meaning in which now we know and we understand how we can represent a number within the computer. Now, how we look at this number from the outside, we can still look at the number in decimal or in hexadecimal. Usually the 2 ways that you are looking at those content of the computers are in this way. And from now on, we go, let me say, we move up 1 layer for the representation. The text. Well, the text yes.
Quando pensiamo di fare una pausa, when you think to do a break?
I was thinking to do at the end of the text.
Okay, good.
Which is another 5 minutes.
Okay.
The text. Well, now that we understand the mechanism, the idea is clear, should be clear, meaning that we just build the table, like as I say, when we were kids and we were playing secret services. We had our secret code where the A was 1, the B was 2, and we were exchanging secret messages with numbers. More or less, the idea is the same, meaning that we build the table in which to each letter we define the corresponding number. And therefore, at this point, we only need, so within the computer, there will be numbers. It is the program that will have to know that those numbers are actually not represent a number, but are actually representing a letter, because the program is dealing with textual information and not with numerical computation. So this is the basic idea behind. Once they're there within a computer, there is no way for a human or for a program to tell whether a byte is a number, is a letter, is a piece of an image, and so on. Within the computer, a byte is a sequence of 8 bits, and it is the program that has to know what is the meaning of those 8 bits. So this has to be kept in mind. So how many bits are needed to represent the Latin alphabet? Any one of you would like to raise the hand and give me the answer? Because what is the reasoning? So first of all, how many letters do we want to represent? Okay, 26, because we are thinking of the English alphabet. But then I say, okay, 26 small letters, but then you need also 26 for the capital letters. So we are already at 52. And then you don't want in a string of text to represent numbers. You don't want to represent commas. You don't want to represent semicolons. and so on, because you want to represent a complete text within the computer. So to give you the answer, we give to the next one. And the first definition that was done for this coding of letters and numbers in a computers was called the ASCII, American Standard Computer Interchange something, I don't remember. And the idea was that in the English alphabet, they identified 95 printable characters, meaning characters that have a graphic symbol. And then another 33 control characters, meaning characters that control the new line and other things. So the first table, the very first table that was defined in the 50s was this ASCII table at 7 bits, in which, as I was saying before, this is very, very easy, meaning you have the character. Let's start with the characters, the one that we see here. You have the numbers. Here you have the capital letters. You have the small letters. And to each number, you assign to each character, you assign a number. So the small a in ASCII table is 97 in decimal or 61 in hexadecimal. And the capital A is 65 in decimal or 41 in hexadecimal. And so this at this point, as I was saying before, once that you have this string of bytes in memory, it is the program that knows that is dealing with a string of characters and not with numbers, and therefore when the program will find a 65, it will show the screen an A, because it knows that 65 is the internal code for capital A. This is the same table in hexadecimal. Now you see how much is compact and how you read. Those are the first 3 bits of the hexadecimal. Those are the last 4 bits. So for example, if I take the capital A in hexadecimal is 4-1. And if I go back, I can easily check the capital A is 4-1 in hexadecimal. But you see how much more compact is representing this table in hexadecimal rather than in decimal. So that is why it's used. In any way, this was defined, this table, in the early 50s and went on until the 60s. Why? When IBM, you remember my chart of before, in the 60s came out with the byte architecture. Which means that all the computers started using the same architecture, and the minimum packet of bits that was being used internally in the computers was the packet of 8 bits. And IBM, together with the 360 architecture, came out with a new code called EBCDIC, that IBM was, I was saying at the time, was having between 80 and 90% of the world market. So somehow was just considering that could do whatever they wanted. So they find their own, let me say, coding for characters within the computer. However, the ASCII words, meaning the competition, the rest of the world, they decided not to give up ASCII, but they decided instead to extend ASCII to 8 bits, because at this point, all the machines were using 8 bits. And therefore, the ASCII consortium said, why don't we extend ASCII to take advantage of the 8-bit so that now we can double our table. And instead of 128 characters, we can represent 256 characters. And so this is what was done. And ASCII now became and still very much used today, because what has happened, I go back one point, EBCDIC is dead, meaning there are still information around in the world on older IBM mainframes, which is coded in EBCDIC. But especially with the arrival of the web and the internet, all the people started using more and more ASCII. So EBCDIC is no longer really used. It is supported by many systems, but is not really used in the internet today. So ASCII, as I was saying, extended the initial table of 128 characters, and since the standards are good, they extended it in 16 different ways. So when we say, you see, I mean, what we have today is this standard called the ISO 8859, which the next letter now says, and why it was extended in many different ways. Because somehow they took advantage, especially to represent, let me say, accented letters, for example, that were not present in the English alphabet, but in the European, many European languages, you would needed a lot of accented alphabets. But they, I mean, when I say they, I mean the community, the consortium of the ASCII, they took advantage to start also representing other alphabets beyond Latin. So there was an extension for Hebrew, an extension for Russian, for Cyrillic, an extension for what was the other one? The Greek. And the Greek, the three main ones that came out, because slowly, I mean, starting with the 80s, computers were really just becoming, let me say, used worldwide. So this is still in use today. In Europe, we use mostly, let me say, Latin 4 or Latin 1. But I mean, operating systems have become smart enough that you do not really need to tell them what system you are using. They will figure out themselves. Now, where we are today? Today, we are instead in Unicode. Unicode started, you see, in the early 90s, when it was clear that computers were becoming used worldwide, and especially with the Far East, meaning China and Japan. And 250, a table of 256 characters was clearly not enough to represent all those characters. So there was this, let me say, this consortium of the main computer manufacturers that defined this Unicode, meaning universal code, that the idea was to incorporate all the existing standards and to be able, let's say, okay, to incorporate all the existing standards. And what is this Unicode? What is the idea behind? Well, the idea is that while before somehow the coding was defined really starting from the machine with the table and how this table was represented in the machine, the idea of the Unicode instead is to start with an abstract notion of a letter or a symbol or whatever. In Unicode, you had, for example, all the musical symbols like the violin key or thing, or you have the alphabet like hieroglyphs or the how it's called, the cuneiform alphabet of Babylon and so on. And so this was the first notion to say, okay, let's take, let me say, in abstract, all the symbols or the letters, or let me say the basic symbol that exist today in the whole world. And let's somehow detach, let me say, the definition of this symbol to which we will assign a name and a number. So each symbol in Unicode has a unique name and a unique number that is called the code point. And the idea is let's decouple, let me say, the symbol from its graphical representation. So you have one symbol in Unicode that can be represented in many different ways that are called glyph. And the many different ways, the example is here, that you have, let me say, in the information, a small a that is represented, or let's say this one, it's you have the capital letter G, which is always this code point here. But however, on the screen, this Latin capital letter G can be small if you have using a 12-point Helvetica, or can be bigger if you have a 16-point Times, and so on. So the way that you see on a screen or you print on a piece of paper your Unicode symbol really depends on the application, on the way in which your program will decide to render this internal Unicode code. But from the Unicode point of view, what is important is just the code point. Well, the name is just for the purpose of the human, but what is important is really Unicode. So this is the basic idea of the Unicode. And how you represent the code point, the numbers of the Unicode. Here, I mean, this is one of the lucky situations in which, despite Unicode being defined by two different bodies, they have agreed on almost everything. Almost everything means that they have agreed on the fact they have agreed. Let me get back here. They have agreed on these numbers. So regardless of the consortium, the code point of all the Unicode symbols are the same. But as I was saying, however, that Unicode consortium, has been the first one and is what we are using, decided they need 21 bits to represent a code number. If you remember the picture of before, 21 bits is about 2 you do not remember, is about 2 giga, 2 billions of numbers. So with 21 bits, you can represent more than 2 billions of different symbols. And today they have defined all the 96,000. So there is really room for expansion. And the idea to use the 21 bits is what, this is what, again, just to know, is that you can use, you can visualize the Unicode space as a number of planes where each plane has 256 columns and 256 rows. And the way that you use the 21 bits of the code, the Unicode code, is that with the first 5 bits, you identify one of 32 planes. With the next 8 bits, you identify one row of this plane. And with the last 8 bits, you identify one column of this plane. So that means that with these 31 bits, you can identify each and every one small cell in this, let me say, virtual space. And why was this idea done like that? Because that was making very easy to assign the existing codes to the Unicode characters, because the basic idea has been that you assign, let me say, the basic rating, meaning the original 7-bit ASCII code, to the first half of the first row of the first plane, which means, if you are following my reasoning, that if I go back one, that all the bits before these 8 bits here are all zeros, because this is the first plane, which are all zeros. This is the first row, which is these are all zeros. And this is the first column, so the first bits are all zeros. So this is the way that, and then the Unicode has assigned, let me say, the codes of the other alphabet going down. And you see, you start just in this first plane, which is called the basic multilingual plane. BMP is the basic multilingual plane. You start having a number of already, let me say, exotic alphabet. You have a number of the Navagari, Bengali, Gujarati, Tamil. They are all Indian. India has about 15 different alphabets with different symbols and so on. So this is the way that we Unicode is done. This gives you an idea of the whole of Unicode. And now the last step is, okay, we are now still in the cloud, because with this plane and the way that we have defined this BMP is in the cloud, is not yet in a computer. So how are you going to put a code point of Unicode into a computer? And here there are 3 possible representations. One, which is called UTF-32, which means the simple one. You take the Unicode value, the code point, and you represent with 32 bits, and you have 32 bits for each Unicode character, which is, given the way that has been defined, is a lot of waste, because most of the Unicode characters here would have the leading bits being all zeros, because they would be mostly Latin characters. So there is another representation, which is UTF-16, in which you represent all the characters in the basic multilingual plane with 2 bytes, and all the other characters with 4 bytes. And this is a little bit used, but not much. And what is really used today is the UTF-8, and you have seen this for many textual information. The UTF-8 is a variable length representation in which each Unicode character can be represented from 1 to 4 bytes. And the assignment of the codes was done in what I would call in such a clever way, so that all the 7-bit ASCII characters are represented by 1 byte. And this represents still today about, they say, from 60 to 80% of the information that is around in the web. So that means that you can represent with just 1 byte. And then you represent all the other characters, Unicode characters, with 2, 3, or 4 bytes. And I will not go into these details, but the idea is here, in which, so this is the binary code of the character. If it starts with all these zeros, you represent, so this is the ASCII, you see those are the 7 bits of the ASCII, you represent with 1 byte that starts with the 0. And all the other Unicode characters that have less and less leading zeros, you represent with this, let me say, increasing number of bytes, and you recognize them because they all start with 1, 1. Because you have to think again, I make like this, no, you don't see my hands, but you have to think that these characters are usually transmitted over the network or received by your computers 1 byte after the other. So they are a string of bytes. And the program receiving these bytes has to understand right at the beginning if what it is receiving is a 1 byte character or a 2 byte character or a 3 byte character. And this is cleverly done with the first bit, because if your program has to know that it is receiving a stream of characters encoded in ASCII, UTF-8. And therefore, based on the first bit of the byte, it will know if it is 1 byte. Then when it says 1, 1, it will know that it is a 2 byte. When it sees 1, 1, 1, it knows that it will be 3 bytes. And when it sees 1, 1, 1, it knows that it will be 4 bytes. So this is more than you wanted to know about Unicode. But now remember that UTF-8 is becoming the de facto for encoding and transmitting information over the network. I will stop here for 15, 20 minutes so that we can have coffee, move a little bit, and we come back, let's say, it's what?
Okay, and I think also what you have done, if actually you have a comment or question, please do it in the beginning of the next.
Yes, if you think it over, if you have something, you can write in the chat, and you can also raise your hand when we start again.
For instance, UTF-8 is something that you find a lot in TI-XML coding. So it's something that you find in the beginning of the TI header. And so you can ask, okay, why on earth there is UTF-8 in the beginning of my text is because of this, for instance, okay?
In other words, again, when you are dealing with text, and in digital humanities you deal a lot with text, I mean, the computer has to know in which way the text has been encoded. And so UTF-8 is becoming more and more common. For many texts that are coming, especially from the US, they are still coded in ISO 5988, the one that you have seen before, one of the 8-bit ASCII. But most of the editor, you will see that you can tell them which format you use. Even Word. For example, if you use Word, and you wanted to save your document in a simple format because, for example, it has to be handled by another program, a Python program or so, in Word, when you save the document, you can choose the format. And if you choose TXT, Word will ask you which format to use. I mean, if you want to save in TXT, but with the format ASCII or in the format UTF-8, or rather I think it gives you 3 or 4 possibilities to choose from. You can check. You take any Word document and then try to save in TXT, and it will open another Windows asking you which format to save. Okay.
Okay, let's see. So now there is 5 to 11. Let's see.
5 to 11, 11:15.
15 past 11, okay?
11:15, okay.
Good break.
Thank you. See you later.
Thank you. See you later. In any case, we keep everything open. I will just switch off the camera and the microphone.
Everything is stay open.
Yes, we stay open.